So I would like to introduce you the first speaker of the day. His name is Andrew Stone. Andrew is a developer of Bitcoin Unlimited. He has been an investor in Bitcoin since early 2012, and he is currently the software architect at OpenClovis Incorporated, a company that provides clustering and high availability software to telecoms, aerospace, and defense equipment manufacturers. Andrew is going to talk to us today about a technical application called expedited forwarding of blocks in Bitcoin Unlimited. So without further ado, I'll hand it over to Andrew Stone. Take it away, Andrew.
Great. So I'm going to talk about expedited forwarding, which is a packet forwarding optimization technique, and also a little bit about Bitcoin Unlimited, the client. So let me just start with this. I think some of you already know what Bitcoin Unlimited is, but I think perhaps some do not. So let me just move through. First, Bitcoin Unlimited is not about an infinite block size. It's actually more about unlimited choice in block size. We basically believe that if we enable market-driven forces, then these forces will act ultimately in the benefit of Bitcoin and solve many of the problems that that other people feel need a lot of magic numbers and software intervention. Another key thing is to essentially acknowledge that there is a human's role now in the Bitcoin network. I think that traditionally Bitcoin has been about removing humans from, a payment network, and that makes a lot of sense. When humans are in the role of, when the human help causes the network to be slow, corruptible, and error-prone. And this happens when humans are in positions of power. But I actually don't feel like I need to even convince you that humans should be part of the network. I just think it's actually a reality. If people can optimize the network to create more profitability for miners, then they will be a part. And this is sort of essentially Bitcoin growing up, right? In data centers, for example, headcount or OPEX, operational expenditures, is actually calculated simply as a function of the CapEx or capital expenditures. In other words, the number of machines that have been purchased and deployed into the network. So large telecom networks just assume that these networks are going to be monitored at all times by people. And the simple reason why is because they're very important networks now, and a lot of money is riding on their successful operation. So in fact, at the same time, this is not actually a crazy idea for Bitcoin. The very Coinbase reward system concept of transaction fees is actually essentially an invitation for people to join this network and, make capacity planning decisions based on the price of Bitcoin and their, ability to deploy hardware cheaply. And so the truth is too, in the past, humans did get involved. As we know, mining had a situation with slow block propagation causing orphans. The relay network was created. It's a centralized block and transaction propagation network. And so in this case, perhaps, people got involved and the outcome wasn't spectacular because this relay network is controlled and administered by a single individual, and it's a single centralized network. So by chasing greater profitability, sometimes decisions can be made to adversely impact some of the security guarantees of the Bitcoin network. And expedited forwarding kind of attempts to address this problem. Let me pop to the next slide. So you might say, why don't we do all this work in Bitcoin Core or, well, Unlimited actually existed before Classic, but maybe XT. And the reason why is because actually having competing clients is very valuable. First of all, you know, the world basically works via groups of people in cooperating and also groups competing. Simple examples of this are, you know, the startup culture in the world with different people coming together to create companies which then compete against each other. And also, you know, the Olympics, right, is a simple example. Any professional sports team. And actually, it turns out that you can kind of see things like evolution or even cellular differentiation as combinations of competition and cooperation. So actually, it might shock some of the more, I don't know, extreme people in the community, but you know, Bitcoin Unlimited actually cooperates with our, you know, frenemy Bitcoin Core. We actually periodically rebase our software on top of their latest release. They do, you know, excellent work, and we, you know, run a more democratic method to determine, you know, what features should go into our subsequent releases and which ones should come out. And we also offer all of our software free, you know, in a liberal license. So like Classic and XT has taken our XThin feature, and you know, it was available for Core. They chose a competing feature called compact blocks, and it remains to be seen whether that decision was for valuable technical reasons or whether, you know, it was simply an inefficiency in the way things happen today. And then obviously, I think a lot of people have talked about how different clients can attack different users, right? One of the main features of Bitcoin Unlimited is that it kind of separates the block size issue from the rank and file user. So if you're not a miner and you run Bitcoin Unlimited, then no matter what the miners ultimately choose to do in terms of the block size, you won't have to upgrade your software. So in that sense, I don't want to say that Bitcoin Unlimited is for end users, because it will work great for miners as well. But if you are just running a full node, then you might it might, you know, make your life a little bit easier. All right. So before I talk about expedited forwarding, first I want to talk about the Bitcoin Unlimited network. So we run a network of 8 or 9 nodes, and this is like a worldwide network, ranging from Asia to North America to Europe. As you can see, we're missing, you know, Africa, South America, and Australia, and Antarctica, I suppose. So if you happen to be running a node, by the way, in those areas, and you would like to help us out, then I would really encourage you to contact me via email. Now, so this network that you see here, which Andrea is going to talk about in much more detail, but I just want to show that all of these nodes in my testing were running in the existing Bitcoin network. They just look like normal network nodes. They have hundreds of connections to unknown other, you know, Bitcoin nodes. But also we've, you know, explicitly pinned up a few connections, which you can see via these black lines. So these connections, depending on my test, will either be running normal XThin or you know, standard blocks, or they might be running these expedited blocks. So as you can see, we basically have a 3-tier network here, which I call our broadcast network. and there are some redundant links connecting the entities. And the idea is to push blocks as fast as possible out to as many nodes as possible. So that's the network that these tests are run on, always in the live Bitcoin network with no limitations on the behavior of the nodes. So moving right along, this is essentially the expedited editions. And what I mean by that is there's a pull request out there which we call expedited, and this is what it adds to Bitcoin Unlimited. First is some more detailed statistics reporting, which I won't talk about a lot here, but that will underlie some of the decisions that the expedited network needs to make. Then a request manager, and then finally the expedited forwarding. The first thing I want to talk about is the request manager. These features are made to solve very specific problems that we discovered in the network. So this is a graph of the propagation of blocks through the entire network from the other side, from the China side of the Great Firewall of China, or the GFC, I'll call it from now on, all the way out to nodes in like Europe or the US. And what we see is a lot of good stuff. Most of the blocks come relatively quickly, but we have this long tail of slow blocks. Okay, you can even not receive a block for 60 seconds. Obviously, this is insupportable for miners, so the request manager was made to solve this problem. And what it basically is it's a reworking of the networking code. And basically, we create a table which keeps track of information about blocks and transactions that the node does not yet have. So on the right of this table, you can, on the right of the screen, I mean, you can see this table indexed by, the hash of either the block or the transaction. And the data consists of the current sort of state of the request. So I have a few examples here. H1 is unrequested, H2 has been requested from one source, and H3 from two sources. And then also we record every single node that has indicated that they have this data. So we keep track of all the potential sources. The network receive code was changed. Simply update this table when IMs come in. IMs, I think we talked about this. Presenters talked about this yesterday. IMs is basically a message that is an inventory message that says, hey, I have this data. You send it out to, you broadcast it out to all the nodes you're connected to. Then on the request side of the network, all of a sudden we can ask and answer the following questions. Should I re-request an object? Who has the object if I need to re-request it? Who has it as an extend? So that's advantageous because extend entities can supply the block with much smaller bandwidth. Who is likely to provide it quickest? So we keep track of latencies between requests and responses for both transactions and blocks. And am I making too many requests to a particular source? So these are the sort of questions that you can now answer when deciding who to ask, what source to request data from. So this is what the old and the new networking protocol look like. And this is slightly different than the diagrams you've seen in previous presentations because I'm looking at the case where we have misbehaving clients. As you saw in that graph, the long tail happens to very few blocks, but the blocks it happens to, the effects are pretty significant. So on the left side, this is what the original Bitcoin code looked like. You receive an inv, you send get xthin or get data, and then the middle is kind of like the other node who's responding. So let's say that it responds very slowly, or there's a TCP timeout, and so you just kind of trail off and do nothing for many seconds. And then as other nodes indicate that they have that data, the old code would just drop these invs as being duplicates. And then you finally time out and give up, and then hope that another inv actually comes in. This last part, I think, is a very dangerous issue in the sense that there's a probably theoretical attack vector in which you could, if you had an entity that made basically one connection to a majority of the nodes in the network, it could quickly, and it gets an early transaction that it wants to squelch, it could send out an IM to basically all the nodes in the network, and then fail to forward the transaction, and then by the time the get block timed out, all of the other IMs would basically be aged out of the network. And so for transactions at least, you would not, like that transaction would not get forwarded until the original client attempted to rebroadcast the transaction through the network. So it's a way to significantly delay the propagation of a specific transaction, which kind of gets you into censorship a little bit. Although it seems like a lot of these attacks, it seems like a lot of effort for a small data. But the request manager forwarding works in a different way. On the right side, what basically happens here is you receive an inv, add it to the request manager, and then loop, right? But if you have never requested it, or you requested it, that should be greater than n seconds ago. Oh, I see. It's saying if you requested it less than n seconds ago, then loop back to the top. Otherwise, drop through, and we're going to choose the best source for the data, which by answering those questions in the prior slide, and then you can run get xthin or get data. And now let's pretend that that data source, sends the transaction or block slowly. Then just a few seconds later, I currently have that configured at 2. We'll send the request to another node, right? So it simply is a way for the system to be a little more impatient about poorly behaving nodes. It's not really a very complex concept. So that's the request manager. And now I'm going to switch over. So at the end, I'll show you the advantages of these things, but unfortunately, I didn't isolate the benefits of one feature versus another, so I'm going to save that graph until last. This is, so now we're going to switch gears and talk about expedited forwarding. So this is meant to solve this problem. So this is a graph of the unexpedited, so xthin and standard block cross-network propagation. So basically, we're looking at a mean of 2.7 seconds. Really looks like most of the blocks come in at just about 2 seconds. But then you have this, again, this tail here, median of 3.7 seconds. So now you might ask, why is these numbers so much larger than the xthin than was described in the articles that Peter R. wrote, but we all contribute to in the xthin analysis? And the answer is because this data is talking about the propagation across the entire network, not just a single hop. So we're going through the GFC, and then over 2 hops beyond that. All right, so basically, expedited forwarding is, we're basically going to attempt to take this, full network propagation and reduce it dramatically. So this is how it works. The original forwarding worked like this. You receive a block, accept and validate the block, send the inv request, and then send, the get data or get xthin, and then you would, send a, oh, this is kind of backwards, but it doesn't matter. Send a thin block or a block, actually sends the block, and then the original node actually receives the block. So this is like a whole conversation. So what expedited forwarding does is you receive a block, then you validate its difficulty. So the reason why you would want to do that, basically we want to forward the block as soon as possible. But it is recommended, I would recommend that we validate the difficulty. The reason why is because that means that an attacker who creates fake blocks in the hope of flooding the network has to at least hash a block, right? So it's very costly to create a fake block and inject it into the network. So then we translate the block into an xthin variety if needed. If we received an xthin, we'll just forward that along. Otherwise, we translate the standard block into an xthin. And then we just forward that data to all of the nodes we have in our table of expedited service nodes. And after we forward it, then we do the accept and full validation of the block. And then finally, the normal block propagation by sending out an IM. So this is expedited forwarding in a nutshell. So let's look at what that means. If you look at sort of the network as a whole. So this is like a, a depiction of a scaleless peer-to-peer network. And if we take like a expedited overlay network and we put it, inside this, basically without changing any of these links, I just kind of, visually you can imagine as you grab one of the nodes and you lift it up and shake it, right? And then all of the nodes with the direct expedited links would be your first hop, right? And then your second hop are all the nodes that they have expedited links to. And then finally, any additional nodes. So as you can see, this kind of creates, if you're a telecom person, like a minimum spanning tree across the network. But there's some qualifications. It's actually not minimum. It doesn't span, and it's not even a tree necessarily. None of that really matters, though, because unlike with telecom networks, the Bitcoin nodes are keeping track of the data that they have already seen. So the reason why in a telecom network you need a minimum spanning tree is so that you don't have cycles in the graph, right? But any cycles in like an expedited forwarding graph are instantly removed because a node receives a block or transaction it's already seen, so it doesn't forward it again, basically. This is a quick slide on why to have expedited forwarding. The reason why is because if you can catch a block right when it's first produced and broadcast it rapidly and quickly to a large number of nodes, in this case, I'm showing the explosion of every block, every node sending to 6 other peers, then you can, basically these first few hops have a disproportionate effect on the propagation time. Why? Because they are simply added to the total propagation time of all of the nodes, at level 4 or 5. And it's also very important to have a successful early propagation. If you end up having these long timeouts, like we sometimes see, then you're unable to broadcast the data widely throughout the network. If you can't broadcast it widely, then you don't have hundreds of other nodes broadcasting the data along with you, which slows down full network forwarding dramatically. So that's essentially expedited forwarding. So we ran this expedited forwarding with the broadcast configuration through the Great Firewall of China out to London, and this is the data that we got. The minimum to get there was actually 137 milliseconds. The mean was about 0.3 seconds, and the median is about a half a second. So that's actually a very good result. I mean, if you calculate it, it would take about 30 milliseconds for the light itself to travel the distance. So we're kind of approaching, transmission limits. This is an incredibly good result through the Great Firewall of China as well. And I think that, this is just supposition and guessing on my part, but I think that penetrating the Great Firewall of China really requires a lot of redundancy in that some blocks are sent through, instantly and untouched, and others are delayed significantly. So if you, send a lot of blocks, you're more likely to get one through rapidly. Now I just picked London as a representative sample. So here I just want to throw up all of them. So typically, we have two nodes behind the GFC, Shanghai and Shenzhen. You can see, I mean, they're getting the blocks obviously right away. And then Hong Kong, just real quick, again, this is 2 seconds, so it's less than a second. This is your first hop. San Jose is also the first hop, less than a second. And finally, Washington, D.C., London, Frankfurt, all of these nodes are seeing the block. In about a tenth of a second, there's major, significant numbers of blocks. The biggest peak gets you to, less than a tenth of a second, or at a tenth of a second, sorry. But there's also this peak at about a half a second. Let me zoom in on that, because I find that very interesting. Here, so what is going on here? So this is this peak at 500 milliseconds. So this is an area that we're examining. And actually, sorry, I wanted to say one more thing about the original graph. So this graph also shows the advantages of the request manager. The longest block with all kinds of retransmission delays and everything took 6 seconds as opposed to 60 seconds. So we've significantly decreased the worst case. However, I still think there's a lot of work to be done there. We should be able to bring all of this down to less than a second. We should be able to identify and remove the most of the problems that are blocking these block transmissions. So that's the data. Conclusion, it is possible to create a high-performance overlay network within the Bitcoin peer-to-peer network. The expediting forwarding dramatically reduces block propagation times. It's about 8 times faster than XThin, which is about 5 to 9 times faster than normal blocks. And finally, as I said moments ago, in the early propagation of blocks benefits greatly with redundancy, right? And especially through the GFC. And then what I'm going to be working on as time goes on is algorithms to allow nodes to automatically create and join these expedited networks. Right now, it's a CLI command that lets you join. We have statistics to discover, which nodes, other nodes might join based on their latency and you know, what nodes are feeding other nodes' blocks. How much does an initial expedited node broadcast reduce latency across the entire Bitcoin network? So I'd like to kind of look at the Bitcoin network as a whole by running a whole bunch more nodes that do not join the expedited network and measure propagation across the full network to see how much the Bitcoin Unlimited network is helping the Bitcoin network as a whole. And finally, identification and elimination of the long tail in a 0.5-second, bump. And then one interesting thing, I'm pretty sure it'll work no problem. Well, it's not that it won't work, it's that how can we optimize the multi-source problem. So, these blocks are all emanating from China. Now let's create blocks that are coming from, Sweden and another expedited network broadcasting those, and how do those two expedited networks touch each other and share blocks, efficiently and rapidly. And that's it. So let's, I guess, open this up for some questions. We got a good question. All right. Do you know of any flooding attacks that are made possible or more deadly by expedited forwarding? So that's a good question. And the answer is, as I was saying, an expedited node will not forward a block or transaction that it has already forwarded once. So there is no flooding attack that is easier. And then there's also the qualification that we are validating difficulty on the block. So a fake block flooding attack is impossible. I suppose too, you could also choose not to forward transactions that are less than a certain transaction fee, but that would, you would only do that if you believe in the idea of spam. Is this in production already? Do you think expedited forwarding is already helping the network to be more robust? Yes. We've been running this for weeks in the production networks. I think it is probably, that's what I want to explicitly measure, but given that all of those 8 nodes gain a block within, say, 1/10 of a second, and they all have hundreds of connections to other normal Bitcoin nodes, I would imagine that other nodes are gaining blocks significantly faster than before. Non-technical question. You mentioned, this is Free Trader. Great talk, non-technical question. You mentioned BU project is more democratic than core. To what do you attribute this? Yeah, so Bitcoin Unlimited has kind of like a charter, which specifies, a human protocol for making decisions on what software is allowed into or out of Bitcoin Unlimited. Ultimately, there's a vote. The officers have very limited ability to stop votes from happening. I just heard some, comment that I don't think very many other countries are going to allow a referendum on exiting the EU for fear that their people might actually vote yes. In BU, the officers don't have a choice, ultimately, if a member, brings a suggestion to vote, that member can force it to vote. Oh, good, more questions. Could this code be easily ported to Bitcoin Core? Do you think it will be, as its value is proven? Yeah, so Bitcoin Unlimited rebases on Core periodically. So you could simply grab our, diff, our pull request, and merge it into core. It's that simple. When do you expect a new rebase release, given that core CSV soft fork activates in about 10 days? That's Free Trader just asked this. Right, so it's a soft fork, right? So it doesn't matter, does it? Can't we just, run the old versions, right? Right? Isn't that what soft forks do? Yeah, so after this talk, which I've been, working hard on collecting the data, then I plan to focus on rebasing Bitcoin Unlimited. So, in a few weeks. Yeah, actually, the most interesting thing is going to be segregated witness in Bitcoin Unlimited. Obviously, there will be a big vote as to what to do about it in probably the next rebase after the current one. Any other questions?
Yeah, Andrew, just wanted to let you know there's some questions that may come in a chat box because unless you're an attendee, you can't ask questions. So I actually posted a question there for you.
Yeah, okay, let me pop over to those. Hi, so let's see. Did you get help from the Chinese community testing this? Yes, we actually have IP addresses of two, one Chinese and one non-Chinese miner that we can connect directly to get early blocks. So that's how we're getting these blocks from China, very early. However, we are getting those blocks as standard format blocks, and then it's the first BU node that converts it into an XFIN and forwards it. So if there's any miners listening, I would love it if you could run a Bitcoin Unlimited client. We don't have to generate greater than 1 megabyte blocks, of course, or anything like that. Just a standard client, so we can push these XFIN and expedited blocks directly from your node even more rapidly. Let's see, Jerry David. Question. It seems that expedited blocks work to improve the latency. Does it address bandwidth as well? Does expedited forwarding work with other block compression techniques? Yes. So expedited blocks is entirely about latency. In fact, the bandwidth can be a little bit worse. As you can see, in order to pass through the GFC, I was sending the block redundantly from multiple nodes to multiple nodes. And so sometimes if you've configured your expedited network like that, nodes will receive blocks more than once. The thing to understand is even if Bitcoin remains runnable on a Raspberry Pi, does that mean that your high performance node in a data center should behave like it's a Raspberry Pi, right? No. So we have a heterogeneous network now, and we should take advantage of our powerful nodes to move data rapidly and efficiently, and in some cases redundantly, right? Does expedited forwarding work with other block compression strategies? Yes. So any right now I'm forwarding XFIN blocks, but really you could just forward any block of any format.
I think we have a couple more questions in the Q&A box.
Free Trader, is the BU project planning to do a blog post about expedited measurements, like the excellent series you folks did on XFIN blocks? I'll probably take these slides, put them up, and maybe collect a little bit more data to give this a little bit broader audience. I think a lot of on-chain guys are mostly listening today. What do you think BU can do to help encourage new developers to focus on it? Well, I mean, I would love to hear what you guys think we can do about that. We try to do things to encourage new developers. For example, you can bring an idea to the community and they can vote on it without source code, because a lot of companies, they don't have time to write, source code, in a fully working example that will probably just be squelched, right? This was a common problem in the core project. So you can, get basically an agreement that this code will go into, the Bitcoin Unlimited when it's complete before you actually do the work. And I think, features like that create a more open environment for engineers to contribute. I just think that Unlimited is, a new project. We don't have engineers who've been working on Bitcoin since, 2009 or 10 or whatever on the project. So I think it's a little bit about trust, and the longer we're, around, the more people will start to realize that we're, serious. Let's see, Reinhard H. Can my BU node already do expedited comms, or do I need to install a special version? Okay, so yeah, the expedited code is a pull request that's been around for months now, since March actually. So right now, your version probably won't handle expedited blocks unless you compiled it, with this pull request. It will be part of our next release. Free Trader, what is the main forum discussion channel where development of Bitcoin Unlimited happens? We have a Slack, bitcoinunlimited.slack.com. If you contact me via my email address, I can give you an invite. All right.
Okay. Well, it looks like that's all the questions. Thank you very much, Andrew. That was quite interesting.
You are welcome.